Okay, let's get started. Pick a rocket. You've got a spacecraft you want to send to Pluto, pick a rocket. And this is really oversimplified here on how you pick a rocket for your job. But number one, how heavy is your spacecraft? Weight is everything. You try to get your spacecraft as lightweight as possible. The New Horizons is super lightweight. It weighs 1,054 pounds, 478 kilograms. It's about the size of a baby grand piano with a dish on top of it. So it's small and it's lightweight. Okay, how far is it going? The further away you want to go, the bigger a rocket you need. And the heavier your spacecraft, the bigger the rocket. Mars is good. Mars is close. Pluto is bad. Pluto is a long way off. And it's not a planet, so I don't want to go there. I didn't say that. How fast do you want to get there? Let me tell you something that will blow your mind. Scientists, say you're a 25-year-old scientist that just gets out of grad school and you're assigned to a spacecraft project to Pluto. Okay. It's going to take you, in this case, New Horizons, about 20 years from when the scientists started working on it to when it was launched. Okay? And now you were 25, now you're 45. Now it took 10 years to get there. Now you're 55. The data is going to be coming back for years. So you're going to be retirement age, even in a 10-year trip to Pluto like New Horizons was. So that's one of the reasons why, number 4 here, some pockets opened up. How much money do you have? The more money you have to buy the biggest, most powerful rocket possible is what you want to do. If you want this thing you've been working on since you got right out of school, if you want to see that project to completion before you retire or before you die, you need a big rocket. And this is the Atlas V, Series 551, with the New Horizons spacecraft on it in Florida. We've used that rocket before to launch other things, like the Mars Curiosity rover. If you've been here at Astronomy Days before, when we've had a life-size model of the Curiosity rover, that's a big thing. It's the size of a Volkswagen. It's heavy, but we use the same rocket. And New Horizons is small and lightweight. We wanted to use the biggest possible rocket possible to get this trip over with as quickly as possible. The Atlas V, it's the first stage liquid engine in the center of the Common Core is a Russian-made RD-80 engine. It has strap-on motors, these little, where's my other laser? These white things down here are strap-on solid rocket booster motors. And depending on how much power you need and how fast you want to go, you can use anywhere between 0 and 5 of those. For the New Horizons Pluto mission, the Atlas V, for the first time ever, used all 5. And also for the first time ever, the Atlas V for New Horizons has a 3rd stage. So it was much bigger and more powerful than even the one that we sent the Mars rover Curiosity to Mars in. And this is an exploded view of it. There's the fairing. The big bulgy part up at the top is the fairing that we put the spacecraft inside. The first stage, the Russian engine, the fuel tank, the strap-on motors, the connecting pieces. And about the spacecraft. I am going to fall off this stage. Maybe I should just go ahead and step down there. The New Horizons spacecraft, lightweight. It's mostly 7075 alloy aluminum, which is one of the main things they make airplanes out of. And it's got some titanium in it for strength, and titanium's lightweight too, lightweight, low strength. We normally try not to use more expensive metals, carbon fiber composites, things like that on spacecraft unless it's necessary because it's expensive. So normally we try to keep spacecraft as much plain aluminum, aircraft aluminum as possible, and no exception here. Also, it's RTG powered. This is a nuclear powered spacecraft. It's got pellets of Plutonium-238 that simply get hot, and you convert the heat directly into electricity. Well, you use some of the heat to keep the spacecraft warm, but the rest of the heat that you don't need to warm the spacecraft is used to convert directly into electricity. And there are no solar panels on this, as you might notice. The reason for that is it's going to Pluto. Once you get any further than Mars, you really can't rely on solar power because you just don't have enough sunlight. So this is going a lot further than Mars. Mars is 1.5 times as far from the sun as the Earth is, and Pluto is a little bit over 30. The propellant, there's only 170 pounds of hydrazine, rocket fuel, propellant in this with 16 thrusters. The reason that there's so little is because the launch vehicle, the Atlas V rocket, was so big. When I talk about the launch procedure here in a minute, I'll show you that the launch vehicle ejected it into tremendous speed by itself, and that was the plan, so that the spacecraft would only need about 170 pounds of rocket fuel to do little maneuver corrections, and little adjustments, of course. Another way to keep it lightweight. Okay, how do we get to Mars? I'll tell you how Pluto. I'll tell you how we usually get to planets, how we like to get to planets. It's called the home and transfer orbit. And this is where, in a nutshell, how that works is you want to exceed orbital escape velocity of the Earth so that you get away from the Earth, never to come back. You're not trapped by Earth's gravity anymore. But you don't go fast enough to exceed the escape velocity of the sun, which means that what you do is, if you want to go to Mars or any other planet, basically what you're doing is ejecting a spacecraft from Earth and putting it into orbit around the sun. And the home and transfer orbit describes this. And that once you're in an elliptical orbit around the sun, you plan it so that that orbit intersects the orbit of the planet you want to go to, so that your spacecraft orbit around the sun crosses the orbit of the planet Mars, hopefully when Mars is right there. And that's easy. That's rocket science. Simple, easy, fun. Easier than saying quinoa. Okay, but instead of doing that, if we'd done the home and transfer orbit to get to Pluto, it would have taken decades. In fact, it wouldn't have really worked. So it wasn't really an option. So what we did, we got the biggest, most powerful rocket we could get, blasted the New Horizons spacecraft directly from Earth into solar escape velocity, passed right by Earth escape velocity and went into solar escape velocity, which means it's no longer bound. Right soon after launch, it was no longer bound to the sun. It is destined to leave the solar system, fly by Pluto, leave the solar system, and will never come back. We'll go into interstellar space. And this kind of shows what I just said. Okay, the flight plan for New Horizons, really cool. Launched in January 19th, 2006. So there's one other thing we did to gain speed besides use a big rocket, and that was to use gravity assist, the flyby gravity assist of the planet Jupiter. So around this time, January 19th, 2006, there was a short window of about 6 weeks where we could launch it and it would be passing by going to Pluto, passing by Jupiter to get a gravity assist. I'll talk a little bit more about that later. It was called a hyperbolic departure orbit instead of the home and transfer orbit. It went to 36,373 miles per hour directly, right off the launch pad. And that's a record. That's the fastest launch that a rocket has ever done. In fact, we may have been prejudiced watching it launch because we thought this is going to be the fastest launch ever. But the rocket just seemed to leap off the launch pad. So much power, so little weight. It passed the moon in 9 hours. The Apollo astronauts took, 2 or 3 days to get to the moon. It took this spacecraft 9 hours. And it passed the orbit of Mars in less than 3 months, which is 3 times faster getting to Mars than what we normally do to get to Mars with the home and transfer orbit. This is the launch. Cool thing about rockets, all that flame and stuff you see there is a point of distance from the launch of a rocket where the sound from the rocket will kill you, but the flames won't. Rocket launchers are cool. What? and if you get close enough, the low frequency vibrations, you can feel the different organs in your body vibrating. Oh, there's my liver. Oh, there's my pancreas. It's really cool. I get into that stuff. Arrived in Jupiter in about a year, which is crazy fast if you're thinking about a Jupiter mission. I mean, we would love to do Jupiter missions in a year. 2 reasons to go past Jupiter. I talked about the gravity assist, and the other one was a flyby rehearsal. That picture on the background of my slide here, that was taken by New Horizons as it passed by Jupiter. Fantastic picture. It doesn't look really good there, but it looks real good on my computer. And the gravity flyby, when you're flying by a planet, there are several things you can do from flying by a planet. You can, if you fly directly at it, you can crash into it. If you fly a little bit off to the side, you can enter orbit around that planet. If you go a little bit further out, the planet will speed you up and change your trajectory a little bit. So that's what we wanted to do here. And we did. The flyby gained enough kinetic energy from Jupiter's flyby to add 9,000 miles per hour to the velocity of the spacecraft, and took 3 years off of the time that it would take to get to Pluto. And it took that awesome picture. One cool thing about this picture, I'm pretty sure what I'm seeing here is, see a little spot on the top of Jupiter's moon Io? I'm pretty sure, Tony, you might know this better than me, that's that volcano called Tabasco, isn't it? What? Tabasco? Tanashtar. It's called Tabasco. Because I can't pronounce what he said. I've just learned quinoa. But that volcano spews its ejecta hundreds of miles into space. And I thought that was really cool that you can just see that right there in this picture. Or that you can see Jupiter and one of its moons in the same picture. Okay, what happens when you're on, I apologize for this mathy looking graph here, but I'll get back to my music here in a minute. What this tells you is what happens when you're in a spacecraft and you're leaving the solar system. And let me see how I can make fun out of this. This is the velocity, how fast you're going. This is the distance from the sun. And 1 AU is the average distance of the Earth to the sun. So what you can tell by this is launch right here. It's going really fast, and it slows down because when you're trying to, even though you've achieved solar escape velocity, the gravity of the sun is still slowing you down. So it does a Jupiter flyby, and that gives it a boost. The escape velocity of the sun is about down here where I'm putting the laser pointer. So as long as your speed is above the escape velocity of the sun, you're going to be fine, and you're going to leave the solar system, and you'll never come back. Comparing that to another spacecraft that achieved solar escape velocity, the Voyager 1. What? That's 2? Then my slide's wrong. Oh, okay. I didn't do that. Somebody else put that one there. Wasn't me. I knew that. Voyager 2 then. Thank you. You see the same thing. It left Earth and did flybys of Jupiter, Saturn, Uranus, and Neptune. And each time it picked up a little speed, and Voyager's velocity is here, which is about 16 kilometers per second, something like that. And you can see here on this line the solar escape velocity, which the further away from the sun you get, the lower it gets. And this is well above that, so it's leaving and not coming back. Okay, after Jupiter, 8 years before it gets to Pluto. What did it do during those 8 years? It passed the orbit of Saturn in about 2.5 years after launch, passed the orbit of Uranus in 5, passed the orbit of Neptune in about 8.5. And during that period of time, it's not doing much. It's hibernating a lot of that time. I'll go into that a little bit more later. It did a TCM. It does several of those. Those are trajectory correction maneuvers. And I'll explain this like this. Flying through space is like playing golf and football at the same time. The football part is when you're launching a spacecraft at something, a football quarterback doesn't throw the ball where his receiver is. He throws the ball where his receiver is going to be when the ball comes down. So you start out interplanetary space flight like that, like shooting your rocket in the general direction of where the planet is going to be when the rocket gets there, not where it is right now. And then golf comes in where you're not able to do that so precisely. So the ball didn't quite get to the hole. So you have to do a TCM or trajectory correction maneuver. I think New Horizons did 9 of them to pinpoint, because the target at Pluto was a little target 60 by 90 miles. So you've gone 3 billion miles in 9.5 years, and you have to hit a little hole in space 60 by 90 miles. So the TCMs are important. So arrived in Pluto, 9.5 years, flew 3 billion miles, got more than 30 times the distance from the Earth to the sun, and it's 4.5 light hours from Earth. That's 1 million miles a day it traveled. And 4.5 light hours from Earth means that when it takes a picture of something, the signal comes at light speed towards us. It takes 4.5 hours to get here. And if we want to send a command to the spacecraft, it takes 4.5 hours for the command to go out. And I will quote crocodile hunter Steve Irwin. If he were alive, he would be going, woohoo! I think that's a quote from when he was bitten by a poisonous snake. He's like, woohoo, she's a grumpy little thing. And this is a Pluto and Charon taken July 8th when New Horizons was still 3.7 million miles away. Okay, 8 years from Jupiter to Pluto. Sounds boring. What are you going to do in 8 years? Spend a lot of that time hibernating. You save fuel, you rest your parts, you let the plutonium RTGs keep you warm, and you just cruise. Second thing, you can entertain mission control humans by throwing an anomaly, shutting down the main computer, and going into safe mode. It did that. That was very annoying. More on that in the next slide. And maybe do a TCM or 2, 9 for giggles. What I was just talking about, space flight is like football and golf. Safe mode. New Horizons basically said, I'm afraid I can't do all of those computational tasks at once, Dave, so I'm going to shut everything down. You can work things out with a backup computer while I take a nap. It's basically what it said. And then Mission Control says, Dave who? There's no Dave here. Everybody recognize Hal? Arrival at Pluto. Pluto was oriented like this. The trajectory comes from here, so Pluto is going that way. So Pluto and its moon systems were oriented towards the approach of the New Horizons spacecraft like a bullseye, like a target. Well, you don't want to hit the bullseye, because that's Pluto. You want to fly by and do other things and take pictures on the other side. And you don't want to hit anything at 31,000 miles an hour. The reason I'm mentioning this is a kernel of quinoa at 31,000 miles an hour could destroy the spacecraft. Anything at 31,000 miles an hour, a grain of sand sized thing, can destroy your spacecraft. So when you go on a trip like this, and we're not really sure even if Pluto has a dusty ring system like Saturn, because we haven't been able to see that. So it may have kind of a ring system made out of dust and small particles. That would not be good without some luck to avoid everything. So what we're going to do, or what we did, is the best way to approach this target is to go through one of the orbital paths of one of the moons, because moons in their orbital path, they tend to clear out the debris with their gravitational field. So the most debris-free place that you're likely to encounter is if you go, not while the moon is right there, you wait till the moon's gone, then you go in behind the moon, because you don't want to hit the moon either. Okay, the flyby. It's a flyby. And the most common question that people are asking now is, well, you spent all that money and you spent all that time. Why are you just flying by? Why don't you go into orbit? I'm going to answer that question in a minute before about 50 of you do ask the question. It's a flyby. You've got one shot, one chance, one opportunity. And I promise this is my last musical interlude from Eminem. You only got one shot. Do not miss your chance to blow. This opportunity only comes once in a lifetime. Yo! You did not know that rocket scientists could be rap stars, did you? Actually, you know that they can't. You've seen it. Okay, closest approach, 7,750 miles, about 14 meters per second, which gives the spacecraft only about a day to do its best science, a flyby. Oops. This is an artist's impression of what the flyby will look like. I don't think that was a NASA artist that did that. Oh, you know why it's not a NASA artist? You know what's really stupid about this? Guess what's really stupid about this slide? Europa. That's Europa. Who said that? Ah, yes, you. I should have figured it would be you. It's Europa, moon of Jupiter. So this slide's totally silly. Not even Pluto. Okay, so why flyby? The question I posed a few minutes ago. Why not go into orbit? Couple of reasons. And stick around for years of science instead of one intensive day and then a little bit more science. Two reasons that I can think of. Pluto is small, and the smaller the object is in space that you want to orbit, the lower your orbit insertion speed is going to be. So Pluto's little. It doesn't have much gravity. So the orbit insertion speed of New Horizons spacecraft would have to be just hundreds or just a few thousand miles per hour at the most. We're going 31,000 miles an hour. To slow down from 31,000 to 1,000 would have required a whole bunch of rocket fuel. A lot more than the 170 pounds that's on board. A whole lot. So much that if you back up, the launch vehicle would have had to be much bigger. Well, we don't have much bigger launch vehicles than the Atlas V with all those strap-on motors in the third stage. That's about as big as we got now. Could have gotten a little bit bigger, more powerful, spent a lot more money, but we really couldn't launch that much. So what we could have done was get the biggest rocket we could, a little bit bigger and more powerful than that one, and just make the trip, it wouldn't have been as fast. So the trip would have taken longer. Again, the trip already took almost 10 years, so we didn't want to add any time to that. So Pluto's too small, orbit insertion speed too small. We were not able to launch the amount of rocket fuel it would take to slow down to that orbit insertion speed. So that's why we're flying by into interstellar space. What's next for New Horizons? Future targets must be, it's going into the Kuiper Belt. If you look here at the solar system, you guys probably know that Pluto is at the beginning of a thing called the Kuiper Belt, a bunch of rocky, icy bodies. So New Horizons is going to fly into that. And due to constraints, what I said, it doesn't have much fuel. It's going to find we're going to try to find more targets for it. And some of the constraints of those targets were it must be less off course. Oh, I do check for typos. Off course. It can only make corrections about 1 degree off course from where it's going. It's like, dag nabbit, I wanted to go over there and it is a 1 degree over, dang it, darn it. Not that, course, not curse. Because not fuel remains. And it can't go more than 55 AUs, which is about 55 times the distance, average distance from the Earth to the Sun. It's already about 30. So it could go almost twice as far as it is right now before the plutonium power source gets too low and the distance gets too far and it's not able to generate enough communications contact with us. Here's some of the things in the Kuiper Belt. The Kuiper Belt, we're finding already something that's about 30% bigger than Pluto, and a lot of this other stuff like that. Kuiper Belt's full of that kind of stuff. We're going to try to find a couple of targets for Pluto after it finishes what it's doing now. And that's it. I am ready for questions and answers.
All right, everybody. I have it on good terms that if you give him a big round of applause, he won't rap anymore. All right, questions?
The speed it picks up from going by Jupiter, if you head in toward Jupiter, I see you pick up a speed, but don't you lose that much speed as you go beyond it?
That's a good question, and that reminds me of something that I was supposed to say and I forgot. Because of conservation of energy, physics, when you pick up speed, that energy has to come from somewhere. And it isn't lost again, but Jupiter actually loses some energy and its orbit slows down and changes a little bit of shape because of flyby maneuvers. How much effect is that going to have on Pluto? It's going to be about like if you have a freight train going at full speed and a small bug flies into it. The amount of directional change in speed that the freight train encounters is going to be about like that, almost nothing. But the energy will go somewhere. It does permanently gain that kinetic energy, and it stays with it through the rest of the flight.
So the New Horizons is going towards the Kuiper Belt next?
Yes, right into it.
How do you guarantee that it's not going to crash into anything?
We don't.
Because if something crashes into the Kuiper Belt, wouldn't that cause comets to come towards the Earth?
Oh,
Because
well,
they're
we're
disturbed,
hopefully this spacecraft is not going to disturb a comet and make it come to the Earth and destroy all mankind. That would be not good publicity for NASA, no. But I mean, you know, the Kuiper Belt is fairly sparse, and it's with any luck at all, it can fly through without hitting anything. And with any more luck, it will fly through close enough for something interesting that we can do an extended mission to see something else. Yes.
Wasn't the Saturn V rocket more powerful than the one you used?
Yes, it was, but we don't have any more of those. I wish we did. The Saturn V was awesome. By the way, the Space Launch System, which is our replacement for the Space Shuttle, is going to be more spectacular and more powerful than the Saturn V. It'll be really something you got to go to Florida and see launch. Yes.
This is back to that first question. The gravity of the planet accelerates the rocket, right? That's how it gains speed.
Right.
Why doesn't the gravity of the planet slow it down as it exits by the same amount?
Yeah, take a whack at that.
Just to try to take a whack at it myself. It almost depends on your perspective. You're absolutely right that if someone were standing on the surface of the planet and watched the probe go by, it would seem to leave as quickly or as slowly as it came in. But from the point of view of the sun, the planet, the probe is chasing the planet for a while, picking up speed as it follows the planet in its orbit, and spends less time going away than it does coming in. So it actually spends more time speeding up than slowing down. Yes, it does slow down. It is slowed down by the gravity of the planet. But the planet he's also right in that the planet is slowed down by the gravity of the probe. Not a whole lot, because the probe is very small compared to the planet. But there's an exchange of kinetic energy there. And the probe takes some of the kinetic energy of the planet as it goes out from the point of view of the sun. Does that answer your question? It's a little bit heady.
There's two things to keep in mind when we talk about velocities. Is the velocity relative to the Earth or the velocity relative to the sun?
To the planet or to the sun.
That's two different numbers entirely.
I'm interested in the fuel that is utilized, and we're talking about the radioactive fuel that's used to keep it warm. and then we're talking about the fuel that was used in the boosters. And I'm interested if it's possible to share with us how that fuel is produced, and do we keep it around ready to be used, or is it produced just for this specific mission and then put into play?
Are you talking about the Plutonium-238?
That, as well as the fuel for the boosters.
The fuel for the boosters is the fuel for the, okay, remember there's a common core. I'll just start there and then work all the way up to the fuel. The common core, the center of the rocket, that's liquid, the RD-80 Russian engine and the rest of the engine, the fuel is liquid oxygen, is the oxidizer, and RP-1, which is a really refined form of kerosene, is the fuel. And that's ubiquitous around space flight and military. The solid rocket fuel it's pretty much the same thing as model rockets that you can buy in the store. The oxidizer is ammonium perchlorate. The main fuel is aluminum powder. And the secondary fuel and binder is hydroxy-terminated polybutadiene or hydroxy-terminated acrylonitrile, one of those two. And they're just common chemicals that you just make up as you need them. And the Plutonium-238, is it Sandia or Oak Ridge National Lab, someplace like that, produces that stuff, and it's kind of hard to get, and you have to warn them a decade ahead of time, and they ask you what you're going to use it for. Well, we're going to send a spacecraft to Pluto. So that's a little bit harder to get because NASA doesn't make that. They don't keep that around. It's not useful for anything else.
Anybody?
Did that answer your question? Okay.
Anybody on the second or third floor?
I wanted to follow up on the fuel. Are there any other spacecraft that use that nuclear fuel as well?
Oh, yeah. Yeah, pretty much anything that goes. Oh, the question was, are there any other spacecraft that use that kind of fuel? And I forgot about one type of fuel. Let me go back to this just a second. The fuel aboard the spacecraft is hydrazine. That's a monopropellant. All you do is just excite that electrically just a little bit, and it's just goes on its own. And this kind of goes to your question, most of our vehicles in spaceflight use hydrazine, either as a monopropellant or in conjunction with nitrogen tetroxide as the fuel, as a bipropellant. Those two, you mix them together, they flame up and they look more like a rocket. But hydrazine was first used in World War II by the German V-2 rockets and some of the rocket experiments they were using, and it's still the same thing we use in space. And yes, hydrazine, just about everything we have in space now uses that. It's stable. Liquid oxygen, liquid hydrogen, and even kerosene in a space environment are not stable. You can't store liquid oxygen and liquid hydrogen, so that's useful for launch vehicles. But once you get into space, you need a chemical that you can just keep in a little container, and it's going to stay fine for decades until you need it. It's not going to freeze, it's not going to decompose, it's not going to evaporate. So that's why hydrazine and nitrogen tetroxide are used in space, and kerosene, liquid oxygen, liquid hydrogen, things like that are used for the launch vehicles. And the reason for plutonium has been used in spacecraft that are not beyond the orbit of Mars. Because like I said earlier, up until you get to Mars, you've got solar light, you've got light, you can use solar panels. But after Mars, it gets too dark and you need some nuclear power. But in some cases, there have been spacecraft that have gone to Mars or this side of Mars and have had plutonium on them, if you need more power than what you can get with solar panels.
So isn't it true that we're running out of plutonium-238 because we don't produce it anymore and we're only running on our stockpiles?
I don't know.
What's left?
I've
And
heard
there's a
that.
danger that we won't be able to.
Tony.
So yes, we have been running out of plutonium-238 in the past. It was Los Alamos, I believe it was made at. The Deputy Director of Planetary Sciences at NASA headquarters reported that we had enough for 3 MMRTGs. However, the last couple of years they've restarted production there, so we are, I don't want to say back on track, but we are producing plutonium-238 within the country again, and it's kind of twofold good news there. A, we're going to have to be able to continue sending missions out beyond Mars, because that's what this means. We have one spacecraft out beyond Mars that is powered by the sun, and that's the Juno mission. Everything else requires plutonium. But the other nice thing is previously we bought our plutonium from the Russians, and things aren't going so well right there now. We need to have that capability internally, so there's another Curiosity-sized rover that's heading to Mars in 2020. We have sufficient stocks in hand right now. Well, I don't think you want to hold it in your hand, but we have sufficient stocks to power that one, 2 more, and are creating more plutonium beyond that. So it's kind of a good news story.
All right, we have time for one more.
Follow up.
Why didn't we use the Delta IV Heavy since we used it for Orion? Was it around?
The Delta IV Heavy, it's not enough thrust.
Then an Atlas, so an Atlas is more.
With a 3rd stage and with 5 strap-ons. Right.
With New Horizons leaving after it passes Pluto and going straight on, just literally into what we would consider infinity, because we don't know what's going to happen to her. Is there been any message or anything that has been placed with it so that if in a weird set of circumstances it's discovered by somebody, say thousands of years from now, or somebody that happens to be cruising along like, our Martian friends, would they know would it be a numerical message that would be put there for them so that they would be able to know where it came from,
We've done that before, but I think, is there anything on here besides the ashes of what's his name? You got it? Oh, the next guy that's presenting will have a slide on that. But it's really kind of depressing because it's going to take the spacecraft that we have leaving the solar system now, it's going to take them millions of years to get anywhere because space is just so incredibly big, and even our fastest spacecraft are terribly, terribly slow. One of the analogies, or not analogy, one of these stories I always tell is if you go up into the sky at night and put your fingers around, find the biggest star you can and try to put your fingers around the glare of that star, that's not the star you're looking at. That's, if that star has a solar system, and now we're thinking most of them probably do, that they're all within that glare. It's the glare of the star that you're seeing. It's not the star. So therefore, our fastest spacecraft, this guy, would literally take at least 2 decades to cross from the left part of the glare of that star you see in the sky to the right part. And that's after it's there. At the speed it's going, it would take thousands or millions of years to get to the nearest stars. So it's really not, don't hold your breath.
All right, everybody, hear it for Alan one more time.
Thank you.